All right. Hello, class. Um, I only see 6 viewers, but I'm going to get started anyways just because the lesson is quite long and I would like to have a little bit of time at the end to talk to you guys in the Zoom room. So let's get started. Um, so, first thing I want to do is I want to talk about last time. And what we discussed last time was Coulombs Law, which is the law that tells you the force between charges. And that force is K times the absolute value of Q1 times Q2 divided by the distance between them squared. And the so that's the magnitude of the electrical force. Okay. And then the rule for the direction is that opposites attract, likes repel. Okay. This constant K that appears in the equation is called the Coulomb constant, and its value is 9 times 10 to the ninth Newton meters squared per Coulomb squared. All right. We learned as well that the amount of charge that something can have is equal to an integer times the fundamental charge. All right, and that was because everything is built up out of protons, neutrons, and electrons. And so yeah. And that fundamental charge is the charge of a proton. And the value is very small. It's plus 1.6 times 10 to the minus 19 coulombs. All right. And that was called quantization of charge. Then we went on to discuss electric current. Which is denoted by I. And I is the amount of charge that flows divided by the time it took to flow. The units of electric current are called coulombs per second because it's charge per time, but that is normally just called the amp. Intuitively, electric current is the rate of flow of charge. All right. So today we are going to be talking about circuits, electric circuits. And there are two fundamental circuit quantities. The first fundamental circuit quantity is electric current. The second fundamental circuit quantity, so even though in an electric circuit, charge is being pushed around by the electrical force, according to Coulombs Law, even though that's what's pushing the charges around, we don't normally talk about it in terms of electrical forces. We talk about it in terms of something called electric potential. Which is also known as voltage. So I will almost exclusively use the term voltage because that is what is this concept of electric potential has meaning outside of circuits, but when you're talking about circuits, you use pretty much exclusively the word voltage. Voltage is denoted by the variable V, and what it is a force causing current to flow. So we could think about electric potential as the cause, and electric current is the effect. So if you don't have voltage, nothing is going to happen. You need to have voltage in order to make the charge start to move. Okay? So there's a cause and effect relationship between these two. So effect, cause. The units of voltage are called volts, which is abbreviated by V. So that can be a little bit confusing at times because the variable for voltage is also V. So you can have thing like an expression that says, V equals 12V. So if you were just thinking about this purely in terms of variables, you would cancel out the V's and you would say 1 equals 12. But that's not what this is saying. This is saying that the voltage is 12 volts. Okay, so I think you can tell from context when V is representing a unit and when it's representing a variable. Okay? Voltage is provided by a source. Okay? And so there are a lot of different sources of voltage. There is a power outlet. Okay, you have those in your house. And power outlets in America are 120 volts is how much voltage they provide. If you sometimes in people's garages, they might have tools or equipment that needs more voltage than 120, and so some homes also have 220 volt outlets, usually outside or in the garage or something like that. Okay, so that's for heavy duty equipment. You can also have batteries are a source of voltage. Batteries have voltages that tend to be an integer multiple of 1.5 volts. So for example, a AA battery gives you 1.5 volts. A AAA battery gives you 1.5 volts. A C battery gives you 1.5 volts. A D battery gives you 1.5 volts. A 9-volt battery gives you 9 volts, which is, of course, 6 times 1.5. A car battery is 12 volts. So that's going to be 8 times 1.5. So it's just kind of an industry standard to manufacture batteries in multiples of 1.5 volts. Okay, and the reason for that is that when you are combining batteries, it's important to be able to combine them in combinations where they match up. So you could stack 4 1.5 or you could stack 8 1.5 volt batteries and make it equivalent in voltage to a car battery. Okay, so you can kind of translate between them easily when they're all integer multiples of each other. So when I was talking about voltages of batteries, I said that all of these different batteries all provide 1.5 volts. So what's the difference then? What's the difference between a AA battery and a AAA battery, or a AA battery and a C or a D battery? And the thing is that when a battery is providing voltage, in order to do that, a chemical reaction is taking place inside the battery. Okay? And in that chemical reaction, reactants are turning into products. Okay? Reactants become products. And once all of the reactants have been transformed into products, that is what we would call a dead battery. So the physical size of the battery is representing, how many reactants are stuffed into that space. So a D battery, for example, which is the big cylindrical one, has more reactants in it, comes with more reactants than a AA battery. So it's going to be able to provide the 1.5 volts for a longer amount of time. Okay. So it has to do with how long the battery lasts. Other voltage sources, you could have something like a generator, which is converting chemical potential energy into electrical energy. Generators are going to output 120 volts just because the reason that people have generators is in order to run their houses when the power goes out. So it has to output the same voltage as your power outlets. And then you could also have things like solar panels. And those can be all over the place. So the voltage that they provide depends on the wiring of the solar cells. So, a solar panel, if you look closely at it, it's made up out of smaller units. And depending on how those units are connected to each other, you can get different voltages. The level of voltage that a solar panel outputs depends pretty sensitively. Well, it doesn't depend that sensitively on the level of sun. Okay, so if there's any sun, the solar panel is going to pretty much output a constant voltage. But what does change is the level of sun affects very strongly the amount of current, electric current, that the solar panel can output. So these different sources also have sort of like maximum amounts of current that they can provide while functioning properly. Okay, so what you find with solar panels is that the voltage is pretty much the same no matter what, but the current that you can get from the solar panel changes dramatically. So now we know the two fundamental circuit quantities, current and voltage. So now that leads us to the question of how do we draw circuits? So let's talk about how to draw circuits. So if I draw a line is representing just a wire. Okay, a wire is simply a pathway for current to flow down. All right. Wires, they can bend, so you can have wires with bends in them. You can also have wires that branch. So if a wire branches, here's a wire that branches into 3 pieces. Okay, so you just put a little dot kind of fill in a little dot, and then you just draw the branches of the wire. Okay. You can have switches. So a switch is used to start or stop current flow. Switch is operated by a user. Okay, so a human being, most likely. And so a switch, that's the symbol for a switch. This is a switch in the open position. So current, if you look at it, because the switch is open, it can't jump across the gap. So that's an open switch that is blocking current flow. If the switch is in the closed position, it looks like that. And so that allows current to flow. All right. If the switch is open, does current flow and then stop? And the answer is no. If there is a block, an open circuit, so if there's a break in the circuit, no current flows at all. Okay. It's like a traffic jam. Okay. If there's a traffic jam that is, created a mile ahead of you, if that's where the traffic jam is, if that's where the accident was a mile ahead of you, you are still stopped back behind the accident. You get what I'm saying? So current operates the same way. If there is a traffic jam, the freeway is stopped right here. Everywhere behind it is also stopped. Okay? So there's just no current flowing whatsoever. So these are switches. There are things like light bulbs. So this is kind of that's the symbol for a bulb. So you have the curlicue, which is the tungsten filament, and then you have the glass bulb itself. The symbol for a battery is long line, short line, long line, short line. Why is that the symbol for battery? Or you could also just use this for any source of voltage. Why is that the symbol for battery? It's because the very first batteries that were created were made up out of, were kind of had like a sandwich structure. So they had two different types of metal, and they were stacked in alternating. So it was like copper and iron. I can't remember what the two metals were, but you had stacks of copper and iron, and then copper and then iron, and then copper and iron. And so those were the first batteries. And so this is kind of referencing that. Batteries, as you know, have positive terminals and negative terminals. So the longer line is the positive terminal. Typically, you would write what voltage that battery is providing next to it. So you would say 1.5 volts or whatever it is. You don't need to put the negative sign over on the other because it's sort of obvious that if this side is positive, then the other side is negative. Sources push current out of their positive terminal. So current flows out of the positive terminal. That's the direction that it will flow. All right. So what if we had, let me just draw a really simple circuit. Okay. So I want you to think about, if you were actually making this circuit in reality, how many wires would you need to do that? So think about it for a second. And if you think about it, I hope you will arrive at the answer 3 wires. Okay, so why is that? You have a wire here, you have a wire here, and you have a wire here. So this is a 3-wire circuit. It has 3 things in it. And as it is right now, the battery would like to push current out of its positive terminal, okay? But it can't because the switch is open. So nothing is going to happen, all right? The battery doesn't run out of voltage unless it's outputting current, okay? So the battery is not draining itself right now. When the chemical reaction is only allowed to proceed if the 2 ends of the battery are connected to each other through the circuit. So there's no chemical reaction happening inside the battery right now. You close the switch, though, and move it into the closed position. Now the positive terminal is connected to the negative terminal through the circuit. So now that chemical reaction starts to proceed. And as it proceeds, current flows out of the positive terminal through the switch, through the light bulb, and then back into the negative terminal of the battery. And in the process of current flowing through the light bulb, that current gives up its energy, which is kinetic energy, by the way, right? You have moving charge, and it's the motion of that charge bumping into the tungsten in the filament that causes light to be produced, okay? So light will be produced. So a major question then is, how much current will flow? Okay, and before I answer that question, let me answer a sub-question. Why would we want to know this? Why would we want to know the current? Okay, so I can think of 3 reasons off the top of my head. One reason is that if this source of voltage is representing a battery, then the amount of current that's being asked is determining how quickly that chemical reaction is happening inside the battery, which is telling you how long the battery will last for, okay? So current is related to how long the battery will last. That's important to know. It tells you how often you're going to need to buy new batteries, or how often you're going to need to recharge the battery, or whatever. If this is not representing a battery, but it's actually representing a source like a power outlet, power outlets, obviously, they just last forever, right? They give you, as long as you plug something in, the current will keep flowing from a power outlet. However, the amount of current that's flowing is telling you basically how quickly your electrical bill is adding up, okay? So the amount of current that you're drawing is giving you an idea of what the electrical bill would be. All right. And a third reason is we talked in the last lesson about how when the current is flowing through something, the electrons are bumping into stuff. So they don't just flow perfectly smoothly. They bump into things, boing, boing, boing. And those things that they're bumping into, when they get bumped by an electron, they start jiggling, and that jiggling is heat. Okay, so electric current flowing produces heat, and depending on the amount of current, if the wire is thin, it cannot carry as much current, okay, without getting extremely hot, which is, of course, a fire danger. Okay, so it has to do with safety. So the amount of current that flows determines how thick the wire needs to be in order to safely conduct that current without danger of fire. Okay, so it tells you about the thickness of wire that you're going to need. All right. So if you've ever opened up a car hood and you've looked at the car batteries, while they don't produce a lot of voltage, they are able to output a ton of current. Okay, and that's why they're so big and so heavy, is because they have the ability for that chemical reaction to happen extremely quickly. And the wires connecting the car battery to your car are really thick. Okay, and the reason that they have to be thick is because they are going to carry a lot of current to start the motor. Okay, so how do we calculate how much current will flow? And we do that using something called Ohm's Law. Okay, and Ohm's Law is V equals I times R. So this is one of our main equations for today. And V represents the voltage of the source. Be it a battery or a power outlet or whatever. I represents the current flowing out of the source. And R is a parameter of the circuit called the circuit's resistance. Resistance of the circuit. Okay, so depending on how you have built the circuit, it will have a different resistance value. So if I take this equation and I divide both sides by R, you get V over R equals I. And so what we can see is that as the resistance increases, because it's on the denominator, making the denominator bigger is going to make the fraction smaller. And so that's going to make the current go down. So more resistance means less current. So basically, in order to know how much current that's going to flow, we need to know what is the resistance of this bulb. Okay? The units of resistance are called ohms, which is denoted by the capital Greek letter omega. Okay? And if you remind me when we're in the Zoom room, I will give you guys some ohm puns. I like to talk about ohm puns. All right, so there is something called a resistor. Okay? And a resistor is anything in a circuit, I'll abbreviate circuit with CKT oftentimes, that provides resistance. So it could be something useful, something that's doing a useful task. For example, an appliance is in some sense a resistor, right? Because it's providing resistance to the circuit. It could be a light bulb. It could be an electric motor. It could be whatever. Something that's so it's doing a useful task for things outside the circuit, but from the perspective of the circuit, we would just call it a resistor. Okay. And then you also have resistors that do nothing, and their only purpose is to control the flow of current. Okay, so controlling the and this is just your first introduction to circuits, but if you were to go study this further, and you want to design a circuit to do something useful, you need to be able to control the amount of current that's going to flow, because that current might represent a signal. For example, if you speak into a phone, you say hello, blah, 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 blah. That voice, the sound of your voice is transformed into an electric current, and that electric current, the size of that electric current is representing your voice in an electrical sense. So you need to be able to control the flow of current if you want to use the current to represent information, for example. So when we're talking about a resistor that is simply controlling the flow of current, we represent it by a jagged line. So the reason that this is the symbol that is chosen is you can imagine that if you were walking along a wire, along a path, and that path had a bunch of turns in it, jagged turns, that would be annoying, okay? It would slow your progress. So this is representing sort of a jagged path that would slow your progress. So that's why that's the symbol for a resistor, and then typically you would write the value of the resistance next to it. So that leads us to the idea of the basic circuit. So the basic circuit would be one where it just has a source of voltage and then a resistor. So 12-volt battery, there's the positive terminal because it has the longer side. And then let's say this is a 2-ohm resistor. So this circuit would need 2 wires, okay? Because you have the wire that goes over the top, and you have the wire that closes the circuit and goes down underneath. So the current is going to go out of the positive terminal of the battery, through the resistor, and then back into the negative terminal of the battery. All right? So the question is, how much current is going to flow? This is a really simple question to solve because we just use Ohm's law. So the resistance of the circuit is 2 ohms. Okay. So I'm going to replace R with 2. And then the voltage of the battery is 12. So dividing both sides by 2, I get that the current that's going to flow is 6 amps. All right, so very simple. But most circuits are not the basic circuit, okay? Let me show you. I will show you an example of a circuit that is not a basic circuit. Here's a book, Microelectronic Circuits. You can see I read about half of it, and then this is a thick book, and I don't know, I lost motivation. But let's pick a random page. Okay. So if we just look at a random page, you can see circuits with various resistors in there. Okay. This is another symbol for a source right here, that circle with a plus or minus in it. This right here, that is the symbol for a transistor. So anyways, my point is that circuits very rarely have just one thing in them. They have lots of things in them. Okay. And so what if we have lots of resistors? Okay. Well, resistors can be connected to each other in various ways. All right. Resistors can be connected in various ways. And so there are two common ways to connect resistors. The first way of connecting them is called a series connection. Okay, and so in a series connection, you have one resistor right after the other. So let's say that's R1 and R2. All right. Or you could have even 3 resistors in series, which would look like this. So it's kind of like a choo-choo train of resistors. Etc. And so when you have resistors, so these could represent like, different lights in your house, okay? And it turns out that the source of voltage, if we're trying to figure out how much current is the source going to need to output, the source doesn't really see the individual identities of the resistors. It just sees an overall effective resistance of the circuit. So even though a circuit might have multiple resistors in it, from the perspective of the source, it just looks like one big resistor, okay? And so when you have 2 resistors in parallel, it's equivalent from the perspective of the source to a single resistor, which we'll call R sub S. And the value of R sub S is the sum of the 2 resistances. Okay? If you had 3 in series, you just add them up. You just continue the pattern. Okay? Here's a trick to tell if 2 resistors are in series. If you can go from one resistor to the other, without the wire forking, they are in series. Okay? So for example, what if I had two resistors that were connected like this? All right? These two resistors are in series because I could go from this resistor to that by following along this path right here. And the wire doesn't fork. It doesn't branch off along that path, okay? R1 and R3 are in series because I can go from R1 to R3 passing through R2. It doesn't matter that R2 is in the way because the wire doesn't branch off in some other direction, okay? It doesn't split along the pathway from one to the other. If you had something like this, and I'm not drawing the rest of what's going on, so I'll just put arrows here. 1 and 2 are not in series. Even though it's one right after the other, the pathway to go from 1 to 2 has this branch where it goes off. Okay? So the presence of this branch means that they are not in series. Okay? The other way that you can connect resistors is in parallel. So parallel looks like this. You have a wire, and the wire forks. Then you have a resistor in each branch, but only one resistor in each branch. And then the wire comes back together. Okay, so this is R1 and R2. You could have 3 resistors in parallel. So 3 resistors in parallel would just be the wire branches into 3 pieces. You only have 1 resistor in each branch, and then it comes back together. So R1, R2, R3. So again, these resistors maintain their identities, but from the perspective of the source, they are equivalent to a single resistor, which I will call R sub P. Okay. And the formula for R sub P is 1 over R sub P equals 1 over R1 plus 1 over R2 plus however many we have in parallel. Okay. So, and then let me give you a trick for identifying parallel. If you can do a loop in the circuit with only 2 things, those 2 things are in parallel. Okay. So what do I mean by that? A lot of times students get fixated on the word parallel. And they say, well, this resistor is horizontal and that resistor is horizontal, so that's what parallel means. But that's not the case, okay? So for example, what if I had something like this? These 2 resistors are in parallel. So even though one is horizontal and one is vertical, it has nothing to do with the orientation of them, okay? It has to do with how they are connected to each other. So how could I use the trick to tell that they are in parallel? Well, if I imagine walking around this loop, okay, this loop right here, I'm only going to encounter this resistor and that resistor. So those two are in parallel, okay? Let me show you an example where two things are not in parallel, but they almost look like they are. So you might think that 1 and 2 are in parallel because they're both horizontal and they're both, it looks very close to this, but they are not in parallel. Why? Because if I walk around this loop here, yeah, I encounter resistor 1 and resistor 2, but I also encounter resistor 3 right here. So the presence of this third resistor makes it so that 1 and 2 are not in parallel, okay? But actually resistor 1 and 3 are in series, because I could go from resistor 1 to resistor 3 along this pathway, and that pathway has no forks, okay? I could also go to from resistor 1 to resistor 3 along the other path, like going around this way. That path has forks. So maybe I should say, if you can find a path, so it's not that there might be another path from between the two resistors where there are forks in the wire, but if there's at least one path where you can go from one to the other without a fork, then they are in series with each other. So 1 and 3 are in series, 1 and 2 are not in parallel. So let's do an example, and then we'll be done. So what if we have this circuit right here? So we got a circuit with a lot of resistors in it. So we got a 24 volt battery, 10 ohms, 5 ohms, 11 ohms, 3 ohms, 4 ohms, 20 ohms, 12 ohms. So again, these resistors could be representing motors and light bulbs and appliances and things that are doing useful things. So the question is, how much current is going to flow out of the battery? So our strategy is going to be to identify series resistors, identify parallel resistors, and gradually reduce the number of resistors to just one resistor, and then apply Ohm's law with that one resistor, okay? So first thing I notice is that I can't do anything with 11 and 3 because those aren't in parallel. But I see that 3 and 4 can be connected by this wire that has no branches in it. So they are in series. So R sub S is 3 plus 4 equals 7 ohms. And then furthermore, I could walk around this loop right here and only encounter resistors, the 20 ohm and the 12 ohm. So the 20 and the 12 are in parallel. So I have 1 over R sub P is 1 over 20 plus 1 over 12. And then I have to remember that once I do this, I have to invert the fraction to get R sub P. This is the equation for 1 over R sub P. So when I do that, I'm not going to show the math in the interest of time. I get 7.5 ohms. Okay? So now what I'm going to do is I'm going to redraw the circuit. But where there were two resistors right here, I'm now replacing them with only a single 7 ohm resistor. And where there were two resistors here, I'm replacing it with a single 7.5 ohm resistor. Like that. Okay? And this was 10 ohms, 5 ohms, and 11 ohms. Okay. So now I see that these three are in parallel. Why do I know that they're in parallel? It's because if I go around this loop, I have only these two resistors. If I go around this loop in the circuit, I have only these two resistors. And if I go around this loop in the circuit, I only have these two resistors. Okay, so all three of those are in parallel. So I go 1 over R sub P is 1 over 5 plus 1 over 11 plus 1 over 7. And that tells me that R sub P is 2.3 ohms. Okay, and then the 7.5 is actually in series with the 10 ohm. Why? Well, if I go from here to here through this pathway, there are forks, right? There are branches. Like here's a branch, here's a branch, here's a branch, okay? But if I go the other way around the circuit, I can see that I can just go directly from the 7.5 to the 10 with no forks in the circuit. So they are in series. R sub S is 10 plus 7.5, 17.5 ohms. All right, so now I redraw the circuit with those changes. So these two become one single 17.5 ohm resistor. These three become one single 2.3 ohm resistor. Now it is obvious that 17.5 and 2.3 are in series because they're connected by this wire that has no forks. So R sub S is 17.5 plus 2.3, which is 19.8. So now I redraw the circuit one last time. And I see that from the perspective of the source sees a circuit with a resistance of 19.8 ohms. Okay, and it is a 24-volt battery. So then once you've got it to one resistor, you use Ohm's Law, V equals IR. So 24 equals I times 19.8. And that tells us that the amount of current that will flow is 1.21 amps. Okay, so that is my lesson for today. And I actually have an important announcement for the Zoom room, so I'm going to end the lesson.